Well, hello, welcome to Math 315. This is the fourth recording for Chapter 8. And in the previous lot, we looked at Taylor and Maclaurin series, in particular concentrating on the Maclaurin series, where we take the successive derivatives, we plug in naught, and we use these as coefficients along with the factorials for our power series, and that's called a Maclaurin series. So we want to find the Maclaurin series for sin x is my next example. To find the Maclaurin series for sin of x. So we'll work through that here. So we need to work out the various derivatives at 0. So f of x is sin x, f of 0 is 0, sine of naught's naught. You differentiate sine, you get cos. You plug x as naught in, the cos of 0 is 1. So there's my next coefficient. So the coefficients so far are 0 and 1. We now take the next derivative, differentiate it again, cos differentiates to minus sine. You plug in x as 0. The sine of 0 is 0. You take the third derivative, so differentiate minus sine goes to minus cos. And again, you plug in x as naught, you get minus 1. And you differentiate it finally again, you differentiate minus cos. Cos goes to minus sine, so you get two minuses, make a plus here. So you're back to sine of x, back to where you started from. And the coefficient's going to be 0. So you can see from the pattern then, the coefficients are going to go 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. They'll cycle through. So we can write down then the series for sin of x, the Maclaurin series then. The first coefficient is 0 from here. Then we get 0 from here. Then we're going to get 1 times x, and then 0 times x squared on 2 factorial. Well, that'll be plus 1 there, plus 0. Then I'm going to get minus 1 from here, x cubed on 3 factorial, then 0, x factorial, and then we go back to the beginning again, so we're going to get plus 1, x to the 5th on 5 factorial, and so on. So leaving out the zeros, we can see what the pattern's going to be now. We're going to get x minus x cubed on 3 factorial, x to the 5th on 5 factorial, minus x to the 7th will be the next one on 7 factorial, and so on. Now, once again, a couple of things to say about this. This is remarkable because, again, sine of x, we're writing sine of x as an infinite polynomial. There it is. And the pattern is beautiful. It's really simple. It's just the odd numbers. The fact we've got odd powers and odd factorials here, and every second sign changes. Remarkably simple pattern when you think about what we're doing. We're taking sine of x and expanding it out as an infinite polynomial. And this series happens, I'll leave you to check, this series converges for all x. So again, this is how your calculator works things out. If you ask your calculator for the sine of 2 radians, it's got to be in radians, then it'll simply, it's got this built in, the first 10, 20 terms, it'll simply put 2 into here, add up the first 20 terms very quickly. And again, because of the factorials get very big, then these terms are going to get very small, so it will converge very quickly. And you'll get good accuracy by just taking a few terms of this thing. This is also of great use in many applications of mathematics, especially in physics and mechanics, because you often get complicated equations with a sin x in them. And what you often do, what the physicists often do, is to replace a sin x, they just take the first term, they just say sin x is roughly x. And if x is small, then that's true. And so you can often approximate sin x by just taking a little bit of this series, perhaps just the first term, and you get a reasonable approximation. Well, so we've calculated the the series for sine x. The next little bit says take that series for sine x, differentiate the Maclaurin series for sine of x, and find the Maclaurin series for cos x. Remember, because we're allowed to differentiate power series, and so if I differentiate sine, I'm going to get cos, and so I can take the series for sine x. This is what we just did. So sine x is x minus x cubed on 3 factorial, x to the 5th on 5, minus x to the 7th on 7, and so on. So if I differentiate both sides, then sine goes to cos, x differentiates to 1. Now you bring the power down the front, so I get 3x squared on 3 factorial. Then I get 5x to the 4th on 5 factorial, 7x to the 6th on 7 factorial plus dot dot dot. And we can do a little bit of simplification. 3 factorial, it means 3 times 2 factorial. And I can cancel out the 3's, and I can just replace 3 on 3 factorial by 1 on 2 factorial. 5 factorial is 5 times 4 factorial, so the 5's cancel and I just get a 4 factorial. The same happens here, and then you immediately see what the pattern is here. Again, it's a beautiful pattern. You get 1 minus. Now we're getting the even numbers. For the sine, we got the odd numbers, and for the cos, we get the even numbers. And if you think about this as well, you know that sine is an odd function. That is, sine of minus x is minus sine x. And you get the odd powers of x in the power series, which is very nice. And cos is an even function. If you take the cos of minus x, you get the cos of x. And in the power series, you get the even powers of x. This is lovely. And it's also a nice way of remembering the series. Now, in this course, you don't need to memorize off these infinite series. My view is that these are so beautiful, you can't forget them, but you won't need to be able to reproduce these off the top of your head, but these are lovely, lovely infinite series. Well, I've done several examples of Maclaurin series. I'll just do one of Taylor series. I'm not going to do, these are the more general ones where we're expanding not about 0 but about some point. So here we're expanding about the point x is a half. So I'll go through the calculations of this one. These are not quite so pretty, and I'm not going to do too much on these here. So we're going to take the function cos of x and we're going to expand it about x as a half. What that means is we're going to get an infinite polynomial in powers not of x like we did here, but in powers of x minus pi on 2. Now again, we've got to work out the coefficients. So I put pi on 2 in, cos of 90 is 0. I differentiate cos, you get minus sine. You plug in pi on 2, you get minus 1. You differentiate minus sine, you get minus cos. You plug in pi on 2, you get 0. You differentiate minus cos, you get sine. Sine of 90 is 1, so you get a 1. Differentiate it again, you get cos. Cos of pi on 2 is 0. And you do it so you're back to where you started from. So the pattern's going to be 0, minus 1, 0, 1. 0, minus 1, 0, 1. Just as it's very similar to what we had with the sine. So the Taylor series then is, the first coefficient is 0. And then you put minus 1. Now not x this time, but x minus pi on 2. The next coefficient is 0 times x minus pi on 2 squared on 2 factorial. The next coefficient is 1 times x minus pi on 2 cubed on 3 factorial. And then minus 0 times x minus pi on 2 to the 4th on 4 factorial plus dot dot dot. And leaving out all the bits with zeros in them, we just get minus x minus pi on 2 plus x minus pi on 2 cubed, because this one's 0, on 3 factorial, and the next one will be minus x minus pi on 2 to the 5th on 5 factorial plus dot dot dot. So there is the Taylor series about the point x minus pi on 2. Not quite as pretty as the earlier series, but that's just what it is. Why would you want to expand about a point like pi on 2 and not 0? Well, the point is that if you want to approximate cos x by a polynomial, then if you want the values to be fairly accurate near some point, for example, near the point pi on 2, then you expand it about pi on 2. And that means that you could replace cos x with the first couple of terms of the series, and it'll be quite accurate provided you're near pi on 2. And this is one of the applications, one of the things engineers and physicists do. They want to approximate all the time, but they want to make sure it's accurate. And so near pi on 2, the first couple of, if you just took the first two terms, for example, this would be a reasonable approximation to this function near pi on 2. In fact, again, if you've got a graphics calculator, you might like to do something like this. Probably easiest to do it with the sine. So, for example, if you're doing on your graphics calculator or your computer, get it to plot sine of x, and get it to plot, say, the first three terms, and you'll see that provided you're near 0, this polynomial will be pretty close to sine x, the graph of sine x, provided you're near 0. You move too far away from 0, you'll get much less accuracy. Okay, so that's the story there, and I wanted to do one more example also to show you why we need Taylor series, that Maclaurin series by themselves are not really sufficient. So we're going to have a look at fx is log x. Now this does not have a Maclaurin series because you can't put x as naught in, the log of naught's undefined. But you can get a Taylor series for log of x near x equals 1. So I'll just work through that quickly here. So we do the same thing again. There's our function around x is 1. So we put 1 in, log of 1 is 0. I differentiate log of x, I get 1 over x. You plug x as 1 in, f dash of 1 is 1. Now I'll leave you to check the derivatives. If you differentiate 1 over x, this becomes minus 1 over x squared. I'll leave you to check that. You plug x as 1 in, you get minus 1. You differentiate this one, again I'll leave you to check, you end up with 2 over x cubed after you've simplified it. You plug 1 in, you get 2. Differentiate it again, you get minus 6 on x to the 4th. I'll leave you to check that. Plug 1 in, you get minus 6. And finally, if you do it another time, you get 24 on x to the 5th, so the derivative is 24. And so on. I won't do any more there. We'll see if we can see what the pattern is. So log x then has a Taylor series about x equals 1. So here are the coefficients. The first term was 0. The next coefficient up here was 1. So it's 1 times x minus 1. And the next coefficient was minus 1 times x minus 1 squared on factorial 2. The next coefficient was 2, x minus 1 cubed on 3 factorial. Next coefficient's minus 6, x minus 1 to the 4th on 4 factorial. The next one was 24 on x minus 1 to the 5th on 5 factorial. Now we can simplify this a bit. This is x minus 1. Now 2 factorial is just 2, so this is minus x minus 1 squared on 2. 3 factorial is 6. 2 over 6 is 1 over 3. So that collapses down to a third, x minus 1 over 3. 4 factorial is 24. 6 over 24 is 1 on 4. Now we start to get excited. This is 1 here. X minus 1 to the 4th on 4. And now we're seeing what the pattern is. And finally, just check the last one here. 5 factorial is 120. 24 and 120 is 1 on 5. And now you believe the pattern here. So you're going to get, you're getting 1, 2, 3, 4, 5, and so on. And so there's the pattern, and there's the series for log of x about x minus 1. Well, I mentioned here in passing that there's an ancient formula for computing the square root. You may not have come across this before. If you're on a desert island and you haven't got a calculator, then you want to work out square roots reasonably, or we'll get an approximate value for the square root. Then you can use this little funny formula here. It's the square root of a squared plus x is roughly a plus the x over 2a. Now this turns out in fact to be simply the Maclaurin series for this function. So for example, to work out root 18 quickly, you take the nearest square, that's 16, and then plus 2. So in this case your a is 4 and your x is 2. So you get a, which is 4, plus x is 2 over 2 times 4 is 8, which is 4.25. And if you check it on your calculator, the square root of 18 is about 4.24. So it's out by 1 decimal place. So that's one little application of the Maclaurin series there. Well, exactly where do these Taylor series functions converge? Well, this is a very difficult and deep question, which I'm not going to go into. A proper answer to the question is you need a knowledge of complex analysis, I should say, to this question. Requires a knowledge of complex analysis, and it's beyond the scope of this course here. But since the Maclaurin series are also power series, we can simply use the ratio test in some cases to find out where the series converges. So for example, I'm just going to tell you what this hyperbolic cosine is. I don't know whether you've seen these before, but it turns out the Maclaurin series for the hyperbolic cosine, cosh of x, turns out to be this infinite series here. And we're going to prove that the Taylor series converges everywhere. So here it is. If you've not seen cosh before, cosh is just an abbreviation really for e to the x plus e to the minus x all over 2. If you haven't seen that before, it doesn't matter. I'm just giving you this one. We're going to prove this converges everywhere. And we do this using the ratio test. So as before, we look at an plus 1 over an. So we replace, now be careful here, you've got to replace the n with n plus 1. So I get x to the 2 brackets n plus 1. And then 2 brackets n plus 1 factorial. That's the a sub n plus 1. And then invert and multiply to divide by a sub n and take the absolute value. Now again, do the x's first. So you get x to the 2n plus 2 divided by x to the 2n is x squared. And I'm left with 2n factorial. And on the bottom I've got 2n plus 2 factorial, which is 2n plus 2, 2n plus 1, and then all the numbers less than that, 2n factorial. These cancel again. Don't need absolute value because everything's positive, it's x squared. And again, this goes to 0 as n goes to infinity. So the limit of the ratio is always 0, and that's less than 1 for all x. So hence the series converges to cosh x for all x. So there's just an example of, again, of an infinite power series, a Maclaurin series, and it converges back to this function for any value of x. So again, when your calculator wants to work out the cosh of something, it uses the first 10 terms or so, wouldn't even need that many I think, of this infinite series, and it always converges back to cosh x. Well, I don't expect you to memorize any of these ones, but I made a list of some of the common Maclaurin series just to have as reference here. We've actually derived all of these already. So here they are. So here's the series for e to the x. It's 1 plus x squared on factorial 2 and so on. There it is in sigma notation. Sine of x we saw was x minus x cubed. These had all the odd powers and odd factorials. And I've written it here in sigma notation. You might like to check how I got that. There's the series for cos of x, and this is all the even powers and factorials. And there again I've written it in sigma notation. and we also worked out the series for log of 1 minus x we worked out before. These first three converge for all x, any x value you like. You can plug in and nothing goes wrong. This one only works if x is between minus 1 and 1, this particular Maclaurin series. Now you don't need to memorize these, but I've just listed them there for completeness sake. Okay, final little section here. We're going to just look at some examples of how we can use these series. And one application of them is to finding limits. So this is a complicated limit. It's the limit of x goes to 0 of cos x minus 1 plus x squared on 2, all divided by x to the 4th. Now you can do this using L'Hopital's rule. If you put 0 in, you get 0 over 0. And you've got to keep differentiating it numerous, because you have to apply it lots and lots of times, I think about 4 or 5 times before you get the answer out. I'm going to do this using infinite series. So here's the series. It says write down the Maclaurin series for cos. Well, I just looked that up. There it is. And we want to look at the limit as cos x minus 1 plus x squared. So I'm just moving these two terms over the other side, and I'm left with these ones here. This is the rest of the infinite series. So I can replace cos of x minus 1 plus x squared on 2 by x to the 4th on 4 factorial minus x to the 6th on 6 factorial plus dot 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 dot. And I'm dividing this by x to the 4th. And when I divide this term by x to the 4th, I get 1 on 4 factorial. This divided by x to the 4th is x squared on 6 factorial, plus and so on. And now I'm taking a limit as x goes to 0. So all of these terms vanish, and I'm just left with 1 on 4 factorial. And of course 4 factorial is 4b3b2, which is 24. So there's a little application of series to find limits. And the final example is another, again, a very useful tool in mathematics to use Maclaurin series to find integrals. Now it turns out if you try and integrate sine of x squared, it can't be done in terms of the functions you know and love. You can try on your, if you've got one of these things like Mathematica or so on, you can ask it what's the primitive of sine x squared. You won't like the answer. It'll give you something, but it's not recognizable. This can't be done in terms of elementary functions. However, the integral is a perfectly reasonable thing to ask, and we can use Maclaurin series to find an approximation, typo there, an approximation to this sum here. And here is the worked solution of this. So again, we look up the series for sine of x, which we wrote down before. There it is. There's the first few terms. Now we want the sine of x squared, so I'm going to replace x with x squared everywhere in here. So I get x squared cubed is x to the 6th, x squared to the 5th is x to the 10th, and so on. I'm just going to use the first few terms. So if I want the integral then of the sine of x squared, that's going to be the integral of this. So I integrate x squared, I get x cubed on 3. Integrate x to the 6th, I get x to the 7 on 7 times 3 factorial. Integrate x to the 10th, that's x to the 11 on 11, dot dot dot, and I'm going between 0 and 1. So I put in 0, you get nothing. You put in 1, you get a third. Now 3 factorial is 6 7s are 42. You get 1 on the top. And 5 factorial, so 5 factorial is 120 times 11 plus dot dot dot. And I've just taken the first 3 terms. I just took the first 3 terms and I got approximately 0.31028. Now I have a thing called Maple, which does things much more accurately, so I got it to work out the exact value of this, at least to that many decimal places, and look, it's pretty good. It's 0.3102. It differs in this decimal, in the 5th decimal place, so it's pretty accurate. So we can use these infinite series then also to work out integrals. We can take complicated functions that we can't integrate, replace them with a bit of their power series, and then integrate the power series and get approximate values. And so that's the end of chapter 8.